Okay, welcome back to Unit 4 in AP Calculus. Today we are in lesson number 4, and we're beginning our study of related rates, which we will do for a few lessons. A derivative is a relationship. Up until now, all of our relationships have been between the change in the variable y and the change in the variable x. However, when x and y are themselves functions of other variables, we can describe the rate of change of x, y, or any variable with respect to this other variable. This is going to be really useful to us when x and y are changing with respect to time. And those are the kind of problems that I want to look at first. So let's start with this example. Suppose Momo and Appa are standing at a street corner. Momo gets spooked and starts hauling east at a rate of 12 meters per second. Meanwhile, Appa begins traveling at a leisurely 5 meters per second north. Let's express Momo's position x meters as a function of time in seconds. Okay, so Momo, his position x, since Momo is traveling east 12 meters per second, then his position x is 12 times t, where t is in seconds. So then we could find dx dt by taking the derivative with respect to t. The derivative with respect to t of x is simply dx dt. The derivative of 12t with respect to t is 12, because it's 12 times dt over dt, which is just 1. So we know that Momo's dx dt is 12, or we could say 12 meters per second. Well, what you'll notice is that they gave us that in the problem. So it wasn't really necessary for us to do this, but I want you to see how this 12 meters per second is a dx dt. Let's do Appa's position in meters. It should work out the same way. His position y, since Appa is traveling north, is going to be increasing by 5 meters per second. That's the equation for his position north. Then I can say dy dt is equal to 5. So we know that his dy dt is the 5 meters per second. Now I want to point out, in this particular situation, we're kind of assuming that Momo and Appa are starting at the origin, but it wouldn't make any difference if I had said that Appa began, 17 meters north of Momo. When we might have a plus 17 with this position, y equals 5t plus 17. But when I take the derivative with respect to t, the plus 17 is a constant, and it goes away. So either way you slice it, dy dt is 5 meters per second. Now let's express z, the distance between Momo and Appa, as a function of x and y. Well, remember the problem said that Momo is traveling east, and he is traveling, his position east we can describe as x. And Appa is traveling north, which we'll describe that position as y. The distance between Momo and Appa, then, is z. And this makes a right triangle. And we know that the relationship between x, y, and z can be found with the Pythagorean theorem, x squared plus y squared equals z squared. Well, let's find dz dt. Well, we can do that by simply taking the derivative with respect to t. So I have to use the chain rule, 2x times dx dt plus 2y dy dt equals 2z dz dt. Now, I'm probably going to just cancel all these 2's. So if I divide everything by 2, I can get x dx dt equals, plus y dy dt equals z dz dt. Well, if I want to find dz dt, I simply have to divide both sides by z. Okay. So, question. At what rate is the distance between Appa and Momo changing 10 seconds after Momo gets spooked? All right, so now we're being asked not for an equation for dz dt, but we're asking for that specific value. Notice that dz dt is changing in relation to x, y, z, and dx dt and dy dt. So 10 seconds after Momo gets spooked. Well, we know that the x coordinate can be found because remember, we know that Momo's traveling at 12 meters per second. So that was 12 meters per second is equal to dx dt. That's Momo. And we know that Appa is traveling at 5 meters per second. That's the dy dt. So after 10 seconds, Momo is at position 20 meters, because 12 meters per second times 10 seconds is 120 meters. And Appa is at position 50. So if we fill these out, we can see that the x value is 120, the y value is 50, and this is a Pythagorean triple. 5, 12, 13. But 50, 120, 130. So now we know all the values. We know 130, we know 50, we know 120. Usually when you solve a problem like this, we'd actually go back to this equation here. I wouldn't necessarily do all this, but we've already got it, so let's do it. We know that the x value is 120. We know that dx dt is 12. We know the y value is 50. dy dt is 5. And we know that z is 130. So that is the value of the rate of change in meters per second of the distance between Appa and Momo. Now we could try and calculate this, and probably should, but if this was a free response question on the AP exam, we would just leave it the way it is. So first of all, I'm going to divide all three of the terms by 10. Give me 12, 5, and 13. 12 times 12 is 144. Then I've got plus 25 over 13. So this is 169 over 13. So the answer is 13 meters per second. That's the rate at which Momo is getting, the distance between Momo and Appa is changing at that moment in time. Now, in another moment, it's not going to be 13 meters per second, because even though Appa and Momo are traveling at a constant velocity of 5 and 12, that distance, that rate of change in z is going to be different at different times. All right, let's go ahead and take a look at another one. Okay, a pebble dropped into a calm pond creates ripples expanding out in concentric circles. The radius of the outer ripple is increasing at a rate of 1 foot per second. Write a function for the circumference of the outer ripple as a function of the ripple's radius. Well, we already know that c equals 2 pi r. We got the equation right there. So that's basically how we're going to do it. The circumference of the outer ripple is 2 times pi times r. What is the rate of change in the circumference of the ripple with respect to time? Well, I know that the circumference with respect to time is dc dt. So I'll take the derivative of this with respect to t. And I get 2 pi times dr dt. At what rate is the circumference changing when the radius is 4 feet? So dc dt is equal to 2 pi. Notice that I don't actually have to enter the 4 feet for the radius, because the change in circumference does not depend on what the radius is at that moment. Now the radius is expanding, they say, 1 foot per second. So I'll just multiply this by 1. So it turns out that it's 2 pi feet per second. So, unlike the previous problem, where we had x and y in our values, so that as x and y change, z changes, these values are not going to be the same. I mean, I chose a nice, pretty number to make this turn out to be a whole number. The next second, this would be an ugly decimal probably. But this value here is always going to be 2 pi feet per second, because the radius was not in the calculation. And so since it's a constant change of 1 foot per second in the radius, dr dt is constant, and it's just multiplied times another pair of constants. All right, well, let's take a look at the area. Let's write a function for the area of the outer ripple. And again, I like to write this down so you're not surprised when you see it. The AP exam does give you most all the formulas that you need right there on the side of these problems. So area is equal to pi r squared. Well, then the rate of change in area would be dA dt equals 2 pi r dr dt by the chain rule. Isn't that interesting how the area of a circle's derivative is the circumference times dr dt? So what about now when the radius is 4 feet? Well, this does matter. So the rate of change in the area is not constant with the radius. So 2 pi, it's not constant throughout the whole time. It's dependent on both the dt and the radius. That's what I am trying to say. So then it's 8 pi at this moment. In another moment, the radius will be bigger and the rate of change in the area will be bigger. So that is 8 pi feet squared per second. All right, let's look at another one. A tank of water is in the shape of an inverted cone as shown. The radius at the top of the tank is 5 feet. So let's label that. The height of the tank is 10 feet. All right, find the volume of the cone. All right, well, we can find the volume of the cone. Volume is 1/3 pi r squared h. So volume is 1/3 pi times the radius of 5 squared times 10. Well, 5 squared is 25, so that's 250 over 3 pi, and that is in cubic feet. Next, we're asked to find the volume of the water in the cone when the water level is 6 feet high. Well, this is a different situation, right? Because now we don't have the height being 10. We have the height being only 6. So I'll draw that in blue. There's only 6 now. But in order to find the volume, won't we need the radius? Well, I hope you see it, right? I hope you see that there's 2 triangles here. And they are similar triangles. They should have angle similarity. So these 2 triangles are in proportion. I know that this value here has got to be related to this proportion here. So we know that 10, that's the height of the whole thing, right, is to the radius of 5 as 6 is to this little radius r. So we can do all that, but I think you'll see that we can do cross product. 10r equals 30, so r equals 3. Or simply see the relationship that it's half and half. So now we can answer this question. Volume is 1/3 pi r squared, so 3 squared times 6. Well, that's 9 times 6 is 54. And 54 divided by 3 is 18, I think. So that is 18 pi cubic feet of water. All right, we want to find the volume of the water in the cone when the top of the water has a radius of 2. Okay, so this is just another application of that. We know that the relationship in this cone is that the height is 10 and the radius is 5. That's when it's all the way filled up, and so it has to be proportional. So when the radius is 2, we can find the height. Well, that's going to be, let's see here. This number is twice that number, so I'm saying h must be 4, right? So we can find the volume. It's 1/3 r squared, 1/3 pi r squared times h, which is 4. So that's 4 times 4 is 16. So this is 16 over 3 pi cubic feet. All right, we want to find the volume of the water in the cone when the top of the water has a radius of 2. Okay, so this is just another application of that. We know that the relationship in this cone is that the height is 10 and the radius is 5. That's when it's all the way filled up, and so it has to be proportional. So when the radius is 2, we can find the height. Well, that's going to be, let's see here. All right, well, let's write a function for the volume of water in the tank as a function of the height of the water level. So we already know, and we're given the formula, that the volume is 1/3 pi r squared h. But I want to write it as a function of just the height. Well, it's simple. We just go back to what we had before. We remember that when the height of the cone is 10, the radius is 5. So the ratio of the height to the radius is equal to, is constant throughout the whole thing. So height to radius as height to radius. And if I solve this little proportion, we get, I could do a cross product. 10 times r equals 5 times h. So 10r is equal to 5h. What we see, though, is that 2r is equal to h. So that means that r is equal to h over 2. So we can use it either way. Well, since I want the function I want the volume as a function of height, I need to replace r with this formula here. So we'll do that. We'll say volume equals 1/3 pi h over 2 squared times h. Well, that just becomes 1/3 pi h squared over 4, square the top, square the bottom, times h, which is 1/12 pi h cubed. That's the volume as a function of the height. Let's write a function for the volume of the water in the tank as a function of the radius. Well, that's just simply applying the other formula. So I will replace h with 2r. And that gives me 2/3 pi r cubed. Now, don't misunderstand me. I'm not saying that these relationships are the same in all cones, but every cone can be done this way. You can always express the h as a function of r and the r as a function of h. They can be different. Maybe the height is 3 times as big as the radius, or only half the radius, something like that. Okay, water leaks out of the bottom of the cone at a rate of 4 cubic feet per minute. Compare the rates of change in the height of the water when the cone is full of water versus when it is half full in volume. Okay, so we're going to be comparing two different rates of change. Rate of change and the height of the water when the cone is full versus half full. Well, we know that volume is equal to, well, actually I said I know, but I've forgotten already. There it is, 2/3 pi. Oh, that's the radius. We're looking for the rate of change in height, right? We want the rate of change of height, so I need to use the height one. Height was 1. That should be a 12. Height was 1/12 pi h cubed, right? Because we had h over 2 is r, so h squared over 4, 1/3 times 4, 1/4 is 1/12, h pi h cubed. All right. So when I take the derivative, I get dv dt is equal to 1/4 pi h squared dh dt. Okay, so that's the rate of change in the volume. We just need to compare. We need to know the rate of change in the volume. Well, it tells us water leaks out of the cone at a rate of 4 cubic feet per minute. Leaks, so that's -4. Is equal to 1/4 pi. Well, when it's full, so we'll say this is when it's full. When it's full, h is 10, right? So that makes that 100 divided by 4 is 25. So that's a -4 over 25 pi. And that is in feet per minute. That is equal to the rate of change of height, right? The rate of change of height is -4 over 25 pi feet per minute when the cone is full. Well, what about when it's half full? So half full in volume. Well, full, we knew we had the full height, right? But now this is a little bit different. So what was the volume when we had a full cone? It was 250 over 3, right? So it must be 125 over 3. 125 over 3. 125 over 3 pi Yeah. That is the volume when it's half full. Well, that we need to solve that in our formula 1/12 pi h cubed. All right, so the pi's can cancel out. Multiply both sides by 12, and the 12 over 1 will become 4 with the 3. 4 times 125 is what, 500? So 500 is equal to h cubed. So the cube root of 500 is h. All right, so I'm going to, if you don't mind, I'm just going to move all this stuff over. I'm kind of taking up too much space. Now it's fighting with me here. All right, where were you? You were over here. Yeah. Something like that, right? All right. So now that I know that I got the cube root of 500 for the height, I need to find the rate of change. So we know that dv dt, which is negative 4, negative 4, is equal to 1/4 pi h squared. So this will be 500 to the 2/3 power times dh dt. So in this case, dh dt is equal to, let's see here, that's 1/4, so that's a negative 16 over 500 to the 2/3 times pi. Well, which one of these numbers is bigger? Well, you know, I'm actually not sure, but I feel like, oh, I don't know. I guess I feel like this number is bigger, or smaller, excuse me. Let's find out. So I'm just going to throw these in a calculator. We got the first number we had was negative 4 over 25 pi. That number is negative 0.0509 feet per minute. What about the other one? Well, our other equation was negative 16 over 500 to the 2/3 power times pi. That is negative 0.081. So the one where it's halfway down already is actually leaking. The height is changing faster. I'm not sure which one I said it was, but that makes sense to me now that I think about it, because if the radius is smaller, then we have more of the change in volume dedicated to the height. So interesting to see how that works. So it's the height is going to go down slowly at first and then faster because the amount that's coming out volume-wise is constant. All right, let's find the rate of change of the radius when the water level is 6 feet high in the cone. All right, so remember we said that the volume was 1/3 pi, actually it was 2/3 pi r cubed. Let me just double check, make sure that I'm not making that up. I have a tendency to do that. Let's see here, function of radius, 2/3 pi r cubed. Yay. So let's find the rate of change. dv dt is equal to 2 pi r squared dr dt. When the water level is 6 feet high, well, what's the radius when it's 6 feet high? Well, remember that the radius is half of the height, so the radius must be 3. So 2 pi 3 squared dr dt is equal to the change, and find the rate of change in the radius. Well, we're saying it's a constant loss of 4 feet. I'm going back to the previous question. Sorry if I didn't make that clear. So this becomes negative 2 over 9 pi feet per minute. All right, looks like you have some practice problems to do. Let's tell you what, you can do all of them if you want, or you can just do them one at a time. Might be good to do one and then we check. So do practice 4.1 right now, pause video, and then we'll go over it. Okay, so here's practice 4.1. Suppose the quantities y and x are functions of t. If y equals 5x squared minus 6x plus 2, find dy dt when x equals 4, given that dx dt equals 2 when x is 4. So we have this equation here, and we know that y and x are related to t. And that's important. If they weren't, then dy dt would be 0. So dy dt, when I take the derivative of y, equals 10x dx dt minus 6 dx dt plus 0. Find dy dt when x is 4. So dy dt when x is 4, given that dx dt is 2 when x was 4. So minus 6 times 2. So that is, let's see here, 80 minus 12 is 68. And that's units per unit time. Not really sure. If you're on an AP question, they don't give you units, then you don't have to give units back. So dy dt is 68 something per something. Unit x per unit t is what you would say. But you don't have to say that. Water runs out of a conical tank. All right, once again, we're doing a conical tank. Pause the video and give it a try. Water runs out of a conical tank at a constant rate of 2 cubic feet per minute. The radius of the top of the tank is 6 feet. And the height of the tank is 4. So we know that there's this relationship between the height and the radius of 4 to 6. So 6h equals 4r. Or 3h equals 2r if you reduce the fraction or reduce the ratio. So we're looking at volume. All right, so we need to figure out, can we replace R with H or H with R? With the cone problem, you can. Not with every related rates problem. Sometimes you have to do like a product rule and handle it, but I think we can. We want to know how fast the water level is sinking. That's H. So I just need to say that 3 over 2H is equal to R. Excuse me. So volume equals 1/3 pi times 3 halves H squared times H. All right, when we square a fraction, you square the top, you square the bottom. So that's a 9 over 4 times 1/3, which is a 3 over 4 pi. That's H squared times H is H cubed. Now I'll take the derivative. dv dt is equal to 9/4 pi H squared dH dt. All right, we know that dv dt is a negative 2. We want to know what's happening when the height is 4. We want to find dH dt. So this is, let's see here, I'm going to multiply both sides by 4, making this negative 8 equals 9 pi times 4. So that's a 36 pi. Yeah, but actually I'm just going to do this. I could have canceled the 4s right away. Why didn't I think about that? That's embarrassing. I'm going to rewind time here. So the 4s go right away. I didn't even notice that. So it's a negative 2 over 9 pi feet per minute. Height is in feet. All right, next one. A rectangle's width is increasing over time. The rectangle's height is decreasing at the same rate. All right, go ahead and pause the video and answer these questions, and then unpause it when you're ready, and we'll go over them. All right, let's see how we did. A rectangle's width is increasing over time. The height is decreasing over time. Under what conditions would the rectangle's area would the rectangle's area be increasing? Sorry, I should miss the word be. Tend to leave out little words sometimes. Well, we know that the area of a rectangle is equal to length times width, right? We know the width is increasing over time and the height is decreasing. So dA dt. Let's use the product rule. This would be derivative of the first, so dl dt times w plus the second, the first times derivative of the second, which would be dw dt. All right, well, we know that the width is increasing and the height, oh, I used length and width. Oops. Width and height. So I guess my length is my height. Sorry about that. Width and height. Okay, I should use those letters. So this variable here is dh dt. All right, I think I'm back on track now with the right letters, huh? Okay, so now that I've got that, we know dh dt is decreasing. dw dt is increasing. So under what conditions would the rectangle's area be increasing? Well, I don't know. I tell you what, let's just say that it's -1. Okay, I'm going to say that dh dt is a -1 and that dw dt then would be a +1. Well, then if that was the case, I'd have a -w plus length. So in what situations would the change in area be a negative? Well, that would be if w was greater than the length. So while the width is bigger than the, here I'm doing length again. This is height. Height. All right. So -w plus h. So when the width is bigger than the height, we want the area to be increasing. I would say, so if the width is less than the height, area is increasing. And under what conditions is the area decreasing? Well, that would be if the width is greater than the height. And what is happening to the perimeter? Well, yeah, what is happening to the perimeter? What is perimeter? Well, perimeter is 2 times the width plus 2 times the height. So I've got dp dt equals 2 dw dt plus 2 dh dt. Well, what we can see here is that the perimeter is staying constant because these are the same rate. One's positive, one's negative, so that's going to become 0. So the perimeter is constant, which makes sense because the height and width are increasing and one's decreasing at the same time. But area, not the case. We know that the area is going to actually be changing the none when it's a perfect square for that one moment in time. But then once width is less than height, the area is increasing again. All right. Practice 4.4. A 17-foot ladder is leaning against a wall. The base of the ladder begins to slide away at a rate of 2 feet per second. How fast is the ladder's top sliding down? All right, give this one a try. Pause the video if you haven't already, and then we'll go over it. All right, so we have a 17-foot ladder, and that is not changing. That ladder is not growing or shrinking in size. The base of the ladder begins to slide away at a rate of 2 feet per second. So it's going this way at 2 feet per second. And we want to know how fast is this happening. Well, I usually call this z, and this x, and this y. So we know that x squared plus y squared equals z squared. Well, we can actually do this one of 2 ways. We know that z is 17, so I could just put 17 squared there. If you don't realize that and you take the derivative with respect to t, I want you to see what would happen. 2x dx dt plus 2y dy dt equals 2z dz dt. But then at this moment, you've got to realize, well, what is dz dt? How is the z length changing over time? Well, since the ladder is constantly 17 feet, it's not. So this is a 0. And 0 times any of this whole thing is 0. So this whole thing is just gone. which is exactly what you would get if you realized beforehand that that value is constant. And you could just say 17 squared, and then the derivative would be 0. But be careful. Never plug in changing amounts before you take the derivative. They might tell you when the ladder is 4 feet away. Don't plug that 4 in if that amount is changing over time until after you take the derivative. But I can plug the 17 in because it's constant. All right, I'm going to divide everything by 2 and get x dx dt plus y dy dt is equal to 0. I know that the base of the ladder begins to slide away from the wall at a rate of 2 feet per second. So what does that mean? Does that mean negative 2? Well, actually, it's positive 2 because x is increasing by 2 feet per second. And y dy dt, and I'm looking for dy dt. So let's figure out what x and y is. When the base is 8 feet from the wall. So once again, they're probably going to give us a Pythagorean triple. They don't always, but this is 8, 15, 17, right? So 8 times 2 is 16, plus 15 for y, dy dt is equal to 0. Solving for dy dt gives me a negative 16 over 15. Does that make sense that y would be decreasing? Well, I hope so. If we pull the ladder out, this has got to fall down. So negative 16 over 15 feet per second at that moment, but that's not always going to be the same because as you see, it's dependent on x and y. All right, we'll do more of this in the next lesson. So until then, take care.